Welcome to EEE2124, lecture on Arduino dev boards. This video focuses on mastering Arduino development, covering architectures, hardware interfacing, and low-level control for computer scientists. We begin with fundamentals, examining the logic of microcontrollers versus complete systems. A microcontroller, or MCU, is essentially a computer on a chip. It integrates all core components like the CPU, memory, and peripherals onto a single integrated circuit. The MCU is the raw chip requiring external circuitry. In contrast, a development board, like the Arduino Uno, provides a complete ecosystem with a USB interface and standardized headers for rapid prototyping. Next, we will explore the Arduino ecosystem, which standardizes both hardware and software for embedded development. Arduino is an open-source ecosystem that offers both a hardware platform and a software ecosystem. It uses high-level C++ functions like digital write and analog read to simplify complex low-level operations. The development board concept encompasses essential components like the breakout board for pin routing, voltage regulation for stable power, a USB bridge for serial communication, and reset circuitry to control CPU execution. The Arduino Uno R3 is the industry standard. Key specifications include 5 volts logic, a 16 MHz clock, and a DC barrel jack for power. It features 14 digital and 6 analog pins. The Arduino Nano is a compact powerhouse, a smaller version of the Uno designed for space-constrained projects. Critical advantages include more analog inputs and a significantly smaller footprint. The brain of many Arduino boards is the ATmega328P. It features an 8-bit AVR RISC CPU architecture, an efficient register set, and pico-power technology for ultra-low power consumption. Understanding pinout architecture involves logic multiplexing, where most pins serve multiple functions. Pins include digital 0 to 13, analog A0, A5, and various power connections. This diagram provides a visual representation of the pinout architecture for the Arduino Uno R3, showing the layout of digital, analog, and communication pins. Here is a detailed pinout diagram for the Arduino Uno R3, including legends for different pin functionalities such as power, analog, digital, and communication. This scene displays the pinout architecture for the smaller Arduino Nano, which also integrates analog, digital, and communication pins into its compact design. Finally, a complete pinout map and legend for the Arduino Nano, outlining the functions and electrical characteristics of each pin. Let's delve into the power and logic levels. The Arduino uses a 5.0 volts TTL logic level, unlike modern ARM processors. Key constraints include a current limit of 20 mA per I/O pin. Understanding signal logic is crucial. Digital signals are discrete and perfect for buttons, while analog signals are continuous, essential for sensors like temperature and light levels. Since microcontrollers cannot output a variable voltage, pulse width modulation, or PWM, is used. By varying the duty cycle, we simulate analog signals to control components like LEDs or motors. The analog-to-digital converter, or ADC, converts continuous analog input from 0 to 5 volts into a discrete integer range from 0 to 1023. This 10-bit resolution provides approximately 4.9 millivolts per step. Next, we'll explore communication protocols, including UART, I2C, and SPI, which allow the Arduino to interact with other devices and the world. UART is the simplest point-to-point serial communication, using just 2 wires, RX receiver and TX transmitter. Remember to cross-wire them, TX to RX and RX to TX. I2C, or Inter-Integrated Circuit, is a synchronous protocol, also known as the 2-wire bus. It supports multiple devices using addresses on the SDA, data, and SCL clock lines. SPI is the fastest supported high-speed serial protocol. This synchronous master-slave communication uses 4 wires and is often used for high-speed peripherals like displays and SD cards. This summary table compares the key features of UART, I2C, and SPI protocols, highlighting their speed, complexity, and number of required wires. Memory management on the ATmega328P includes 32 kilobytes of flash for non-volatile code storage, 2 kilobytes of SRAM for volatile runtime memory, and 1 kilobyte of EEPROM for non-volatile data storage. Be mindful of the limited SRAM. Comparing hardware, the Nano offers more analog inputs and a much smaller footprint than the Uno. Choose the Nano for breadboards and the Uno for Shield compatibility. Our final section covers the 32-bit evolution, focusing on the Uno R4 Wi-Fi and global connectivity features. The Arduino Uno R4 Wi-Fi represents a quantum leap, transitioning to a 32-bit processor while maintaining 5 volts compatibility. It features a Renesas RA4M1 CPU, an ESP32S3 IoT module, and an integrated LED matrix. The R4 Wi-Fi is designed for the Arduino IoT Cloud, providing native connectivity features like over-the-air updates, automatic networking security, and smartphone interactivity for seamless IoT development. This final matrix provides a comprehensive comparison of the technical specifications for the Uno R3, Uno R4 Wi-Fi, and Nano, allowing you to select the best board for your next project. Regarding computational performance, the R4 is significantly faster due to its ARM architecture, which handles complex floating-point math more efficiently than the 8-bit R3. In memory allocation, the R4's 16 times greater SRAM allows it to handle large data structures, such as string buffers and JSON parsing, that would typically cause the R3 to crash. Key lecture takeaways include understanding the architecture shift from 8-bit AVR to 32-bit ARM, mastering interfacing with digital and analog signals, differentiating between communication protocols, and leveraging the R4 edge features like the DAC and integrated Wi-Fi. Next, we examine the standard build-deploy toolchain. This involves 4 main steps: coding, compiling, uploading, and executing your Arduino sketch. The first step is coding in the Arduino IDE. The official Arduino documentation is your primary reference for the core library, covering all syntax and functions needed for development. For initial setup, every sketch includes the setup function. This function runs only once after power-up or reset, and is used to initialize variables, set pin modes, and begin libraries. Following setup, the loop function runs consecutively. It is the core of your program, allowing the Arduino board to continuously change and respond to its environment. The serial monitor is crucial for communication and debugging. Use serial.begin baud to initialize serial communication and make sure the monitor's baud rate matches the code setting. When dealing with digital and analog I/O, we use dedicated functions. Digital I/O pins use digital read and digital write, while analog I/O pins use analog read and analog write. This example demonstrates digital read and digital write, where a push-button state is read from pin 7 and used to control the built-in LED on pin 13. Here is an example for analog I/O. The PWM duty cycle of an LED is set proportional to the analog value read from a potentiometer connected to analog pin A3. The delay ms function pauses the program for the specified amount of milliseconds. This simple example shows how delay can be used to control the timing of an LED toggle. A major drawback of delay is that it halts all other activity during the pause. For events longer than a few milliseconds, this prevents reading sensors or running calculations. To overcome the limitations of delay, we use the blink without delay approach. In the setup, variables are initialized, including the time interval and the initial state of the LED. The non-blocking loop function uses the millis timer to check if enough time has passed to change the LED state, allowing other code to run simultaneously.